you should now be seeing my Firefox window with the Jupyter Lab notebook in it, the Jupyter Lab interface. So I will back up just a little bit. I'm going to be running doing the tutorial on Data Lab, just so it's a uniform platform that people can follow if they're following along in the recording. I don't suggest trying to follow everything I do in real time here, because I'm not sure how many sessions Jupyter Lab will be, not how many sessions Data Lab will be able to support at once. So just follow along. I will try and go slowly enough that people following the recording can see what I'm doing and follow along with that at their own pace at whatever time. So I'm going to start by showing the GitHub repository front page for the tutorial. The base of the URL is what I have highlighted in the URL thing, in the URL bar. The tutorial itself is buried in a subdirectory here. You can see there's several notebooks in the tutorial directory, and the README has a table of contents that says what the major tutorial elements are and what they contain. So to run it from NOIR Lab, you can go to the Astro Data Lab here. There's a quick start with a create a new account. So if you need an account, you can get one that way. And you can then, once you have an account, you can launch a Jupyter notebook. And that gives you something that looks like this. So the first step will be to clone the GitHub repository with tutorial notebooks in it. So you can start a tutorial, start a terminal. You go to a notebook directory, and that generically has some things provided by Data Lab, but you'll want to have a repository with the notebooks. So go ahead and clone the notebooks.
Eric, can I interrupt you for a second? Eric.
Yes, go ahead.
Did you expect people to log into Data Lab and then do what you're doing on screen? Or did you just want them to clone those notebooks and do them later on their own machine?
I think it would be safer to clone the notebooks and do it later. I'm doing it on Data Lab so that you can follow along later on Data Lab.
I see. But at this moment, you are not expecting people to go to Data Lab.
No, because I'm okay. Uncertain how well Data Lab will respond to everyone on this tutorial trying to hit it at once.
Understood. Thank you.
So now I'm cloning the Rubin Sim notebooks. So now at Data Lab, there's a subdirectory here with the Rubin Sim notebooks. In this left panel of Jupyter Lab, your base directory, there's this notebooks directory. You can follow that, and the Rubin Sim notebooks will appear right there. And of course, you can use your own directory structure if you choose. So you can follow the links. The actual tutorial notebooks are under the math subdirectory and then tutorial subdirectory. And we start with Introduction to Math. And for the sake of, okay, it'll ask you what kernel you want to use because the Data Lab doesn't necessarily have the same kernel we developed it with. The one we want to use right now is this LSST 2021-1013 Pi 3. You do not want to use LSST Sims Math, that's an older version. So you want to use this 2021-1013 and select that. Now, just to improve screen real estate, You can click that folder up there. That'll get rid of the side panel. You can always get it back by clicking it again. So the tutorial notebook begins with some general discussion. I'm going to walk through this diagram to get an overview of some basic concepts that are important to understand when you're actually running the code. So what MAF does is it transforms the output of OpSim, which is a table of visits. So it's a table in a MySQL database or SQLite database with one row per visit, and each row contains things like the time of the visit, the exposure time, the filter, the coordinates, and also some simulated parameters like the seeing, the depth, the sky brightness, that kind of thing. It has per visit information in these rows, one per visit. So it's a great big table of visits. Ultimately, by itself, that's not very interesting to look at. What you want is some way of getting a handle on how good those visits are for your science. And there's two ultimate outputs that are important. You can make plots that represent bunches of visits in ways that make sense to understand visually. There are also summary statistics, which are individual scalars that provide some information on human interpretable information on the quality of the survey. So typical plots will be things like histograms of air mass or maps of depth or things like that. Summary statistics include things like the median depth over the best 18,000 square degrees, that kind of thing. So MAF's job is ultimately to transform this table of visits into these plots and summary statistics. To understand what's going on in the middle here, you should think a little bit about what plots are. So elements of plots represent two kinds of things. Typically, not always, but often in plots, particularly plots of lots of data, there'll be some features of a plot which depend on subsets of the data. So if you're making a histogram, for example, it divides up the data into subsets, as in the different bins of the histogram, and the widths of the bars and the locations of the bars are defined by the definitions of what the subsets are. So some features of the plots are in terms of subsets of the data. Other features of the plots are functions of the data within those subsets. So for example, in a histogram, the height of a bar is the count of the visits or whatever inside that bin. And so there's sort of these two pieces to building a plot. There's splitting things into subsets, and there's actually calculating a value for subsets. The same thing kind of happens with maps, each pointing on the sky. The location of the pixel is determined by what the subset is, and then the color is whatever value you're measuring for that's the subset. So this operation is very similar to a split, apply, combine pattern you see in SQL or pandas or other data analysis things, where you take a large set of data, split it into groups, do something in groups, combine things in the end. So MAF implements this through what are called slicers and metrics. So a slicer is a way of dividing the visits table into subsets of visits. The metrics then calculate values for those subsets. And so the metrics, as a technical term within MAF, are just the bits of code that calculate values on a per slice basis. There's one important difference between slices and the split functions in, say, pandas or SQL, the grouping functions in pandas or SQL, in that a given visit can actually fall in multiple slices. For example, if you're making a map of the sky, you can have a single visit the field of view is bigger than your sampling, and so a single visit will cover multiple pointings on the sky, and so we'll need to fall into multiple slices. So it's actually a many-to-many relationship between slices and visits. In other cases, it will be one visit per slice, but it's not generally true. So a final piece of this is something called constraints, which basically limits the visits you're considering in your plots and summaries. So a typical constraint will limit what filter you're using. Say you just want to look at G-band images. So the constraint will be that the filter is G. So there's these three elements in the first step in the processing: a metric, a slicer, and a set of constraints that ultimately produces values for the metrics and the slice definitions. And then these then get further transformed into the actual plots you want or the summary statistics. And what I've just said basically covers what this text here says. So the typical workflow for how you actually use MAF, you instantiate an OPSIM database object, which just provides an interface to the OPSIM database. And then you create what are called metric bundles. So a bundle combines a constraint, or a set of constraints, a slicer, and a metric. So the things in here. There are some additional things that you can include in the bundle, but they are optional and they have defaults. So ultimately, you create a Python object which combines these three things. And then you do this for as many different metrics as you want to run. And you combine those into what's called a metric bundle group. So if you're, for example, wanting to sample air mass distributions in each filter, you can have metric bundles, one for each filter, so they'll be the same except for different constraints. And then you combine them into a group. And then the group will iterate through all the different things in your metric bundles and calculate the values. And then you can plot the values. And then when you're done, you can also go back and refine the plots, and it saves the various metric values and slices into files, so you can then do further steps here without having to do all the recalculation of these numbers. So now we actually get into the code part. The first cell, if you don't know what it is, don't worry about it, leave it commented out. If you do know what it is, you know whether or not you want it. First thing to do is actually import the Rubinson Python module. This is a bit simpler than it used to be. Rather than having to import individual sub packages, there's an interface to all those sub packages collected under MAF, and so that you can import and use everything just using maf.whatever. The notebook also records the version that was used to run the notebook. So the first thing we want when running our example is a place to put the data. When you compute metrics, it produces files, NumPy data files with the slices and metric data. Also, when you can make plots, it creates PDF files and PNG files. We need a place to put these. This collection of cells just sets up datadir to point to a directory that you can use. You can either specify one, you can set it to your current working directory by uncommenting this, and this cell here just creates a temporary directory that it will use for the remainder of the notebook, but it will automatically get cleaned up whenever the kernel shuts down. So you won't be able to look at it later because it'll be automatically deleted. At the same time, you can run the notebook many times and not have to worry about filling up disk space and with useless data. The next thing you want is the database to work with. The current the new RubenSim actually includes the baseline upsim output, and this function will grab the file name of the baseline on your system, provided you've done that RS download data step that Peter mentioned in the talk we just saw. So here we set the upsim file name, and then we print it, and this just shows where it was when I ran the notebook last. It's helpful to have a run name, just a string that represents the name of the run. This cell is a convenient way of just extracting this element of the file name. So base name splits off the directory from the file, split X splits the file from its extension. And so this cell just provides an easy way of getting a string which labels the name of the run that we're analyzing. Okay, so now we get into actually running a metric. So we set the database interface. It's now just math.opsim database in the file name. Let's just look at the G filters. So we set a constraint, filter is G. Constraints here are literally just fragments of SQL. The data is stored in an SQLite table. Behind the scenes, math runs an SQL query to get the data. Anything you put here gets stuck in the where clause of that query that it uses to get the data. Later on in the notebook, I will show you how to find what columns are on that table so you know what you're looking at and what you can use. Then you need to define a slicer. So remember in the top diagram, we needed a mechanism for dividing the sets of visits into subsets. We're making a histogram of visits in G here by air mass. So we create a slicer, we tell it, I want to slice on the air mass column, and I want to have the bin limits set to these and the bin sizes. So this just defines how we're going to make our subsets of visits. Finally, we need a metric. So it's our operation we're going to perform on each subset. We just want to count the things in the subset. In this case, well, in metrics generally, in general purpose metrics, we typically want to have a column equal something to the column being used. In this case, it doesn't really make any sense. This will just get ignored anyway, but something needs to be there for the count metric. So what we're doing is we're slicing it into bins by air mass, and we're counting the things in each bin, and that's how we're going to make our histogram. So now we make the actual metric bundle, which is what combines the elements into a single Python object. So we give it our metric, our slicer, our constraint, and we assign it a run name. The run name is optional, but if you don't include the run name, then the file names that math produces will be less meaningful. The normal way of actually computing the metric values is to combine one or more metric bundles into a metric bundle group with the addition of the database and an output directory. There are ways to run the values directly on the metric bundle itself. If you do it in a metric bundle group, it optimizes things a bit better and does a lot of the bookkeeping for you. So here we create a metric bundle group from the one metric bundle we made. So we give it a list that's only one long. We tell it what database we're running the metric bundle on and where you want to put the data. Finally, we can do run the run all method on the metric bundle group. What this does is it iterates through each metric bundle in our metric each metric bundle will be included in the group and processes the data from this database on using that metric bundle and writes the output into the data dir. What happens after this run all is run is that each of these metric bundles now include the metric values and the slices. So these values and these slices are now parts of the metric bundle. And finally, we can create a plot. The default plot for the 1D slicer is a simple histogram. So when we ask it to plot all, the metric bundle group goes through each bundle we gave it. It was built with. In this case, there's just one, and it runs the default plotters on each one, given that we haven't specified any other plotters. The close figs is necessary if you want to actually look at it within a Jupyter notebook. If you do it without the close figs, it'll make the plot files, but it won't show up in the notebook. Now, the metric value, if you want to do more than just look at it with the plotting tools, if you want to do whatever Python operations you want on the values, you can get to the values in the slices themselves. So this metric bundle that we made up here, after you run all, the metric values get set and the slicer slice points get set. So these actually have the values for each of our histogram bins, and the slice points include the limits of the bins. So we now can do any operations we want, not just the ones that are defined inside plotters or other things inside math. You can use whatever Python tools are useful to you. When math is run, it dumps both the plots and the metric values and slice points into files in that data directory you specified. These can be reloaded and the metric bundle rebuilt later. So the mechanism for doing that is a metric bundle.load method. This is just a fancy way of rebuilding the file that it made. You can see that the file names it uses are a combination of the metric name, the metric class that we used, the constraint we had, and the slicer we had. So it tries to be smart about how it builds the name. So the math metric bundle load, you give it the file name, and now you have your metric values back. You have your slicer back with the slice points in it. So you can now continue whatever analysis you want. If your constraint is just filter equals something, then math is smart enough to realize that, oh, the metadata for this particular group is just the filter. Now, there's a lot more you can do with math than just this. For example, you can customize the plots. The simplest way to customize the plots is to specify what's called a plot dict, which is just a Python dictionary that defines parameters of the plots. One way of specifying that is to just include it inside the metric bundle when you make the metric bundle. So for example, if we want our plot to be in red, we can specify color as being R, and otherwise it's just the same as what we did above. And when you create the metric bundle group, you run all, you plot it, and you have your plot in R. Now, these plotting in this mechanism really only shows you one simulation at a time, because the plots are tied inside metric bundle groups. You can, however, plot multiple simulations by doing the plot outside the metric bundle group. So to show how to do that, we can grab a second simulation to use. In this case, these 3 cells are just a dance to get access to a second simulation. It starts by looking for it in the data directory. If it can't find it, it checks to see if it's in the location where it would be if you're running it in WireLab. And so you wouldn't have to download it or anything if you're running on Data Lab. And then finally, if it doesn't have it, this cell will actually download it from the archive of runs at NCSA and put it in your data directory. Just like we had a run name for our original simulation, you'll want a name for a run that we're comparing it with, and we extract that the same way. And then we create the constraints, database, slicer, metric, and metric bundle exactly the same way that we created the one for the first plot, so that we can then have comparable data to plot. And the run all is what actually initiates the calculation of the metrics inside the metric bundles. Now, to make the plots, now that we have both of our metric bundles, you create a plot handler. So this is instantiated just by instantiating the plot handler object. You then set which metric bundles you want included in that plot. In this case, we can use our first example and our second example. And then if we plotted them both just like that, you couldn't tell them apart because they would use the same plot parameters. And so you need to set separate plot dicts for each of your metric bundles you set. So you can create a list of plot dicts, which is the same length as the list of bundles that you're plotting, set different colors and set the labels. And then you tell your plot handler, you plot it, you tell it what function you want to use to do the plot. In this case, it's the 1D bin data, and you tell it what plot dicts you want to use. And here you get the 2 plots, and you can see that they're almost the same, which means that the rolling all sky comparison simulation we used results in almost, but not quite the same air mass distribution as the baseline. You can see there's a little difference here and a little difference here. So that's one basic kind of metric that you can show in math. Another one that's particularly common is wanting to look at sky maps. So you follow the same procedure as we did earlier. We just use different slicers and different metrics. So let's just look at R band for the moment. So we set the constraint to R. Again, this is just a SQL fragment. We use a heel pick slicer. So heel pixels divide the sky into small areas that are indexed and have a unique definition. NSide determines the resolution of the division of the sky into the sub areas. So the heel pick slicer defines the areas, and then the code inside that slicer figures out which visits fall on top of which heel pixels. And remember that the slices can assign the same visit to multiple different slices, and so a visit can cover multiple heel pixels. If you want to look at depth, there's the COAD M5 metric. So it's the 5 signal limiting magnitude of a COAD of all the visits that are in the slice. So now we can calculate the metric just the same way we did before. We create a metric bundle that combines our metric, slicer, constraint, and run name. We create a metric bundle gloop that includes our metric bundle. We tell it what simulation we want it to run on and where to put the data when we're done. We hit run all, and that actually computes the depth for all of the heel pixels. And then if you use plot all, it uses the default plotters for the HeelPix slicer to create a map, and in this case, a histogram, because those are the two default slicers that are included for the HeelPix slicer. And once again, we have direct access to the metric values themselves as a masked NumPy array. And we have the slice points. And so we know that, oh, we've assigned slices to an NSide HeelPix map with an NSide 64. SID in this case are the HeelPix IDs. And then we also have the coordinates of all the heel pixels. And so we can see for any given heel pixel, we can just index this masked array to get the magnitude in that heel pixel. Now, I should stop for questions now. So before I go on, anyone have any questions? Okay.
I'll just confirm we can all hear you if you're wondering if you
Right.
Yeah, it's all great.
Okay.
It's all great, Eric. And just to let you know, I am following along at home on the IDF and I am keeping up with you.
Oh, awesome. Okay. So remember I said earlier that once you run these metric values and slices, you can continue to fiddle with the plots later. So you can do that by taking your existing metric bundle we have here and using set plot dict to change parameters in the plot dict. So the parameters for the projection of the sphere in the heel in the representation of the sky are one of the things you can customize. So the default map projection used is a Mulbeady projection. By default, it puts RA0, DEC 0 in the center of the projection, which is what gives the line of the equator in the middle. If you would rather have the South Pole in the center so that you have sort of the minimum distortion area of a Mulbeady map in the middle of the representation on the sky, you can set ROT, which sets the coordinates for the center and the rotation of the center. So you just set your plot dict. You then set the plot function you want to use. In this case, let's just do the map. Let's not include the histogram. And that's HeelPix sky map. And then plot. And then you have your plot with your modifications to it. So far I've shown you a lot of stuff to do with the plots. I haven't really mentioned summary statistics yet. So we can go on to that next. I can find my spot. So summary metrics are really just regular metrics. They can be called, the way in which they are written and they are called is exactly the same as a regular metric, except that they take metric values and further transform them down to individual scalars. So it's one more thing we can add to our metric bundle is a list of the summary metrics we want to use. So let's continue with our heel pick slicer. So we're looking at coad depth as a function of coordinates on the sky. And over those heel pixels, let's get the minimum, the median, the maximum, and then the RMS of the limiting magnitude. So you define a list of the different summary metrics that we want. We include those summary metrics when we're building our metric bundle. We run our metric bundle group exactly the same way as we have been. When after we do the run all, we've done a run summary all, which creates the summary metrics in addition to making the metric values and slice values. And then the summary values are part of the metric values. So you can just look at them as a dictionary in that metric bundle. Furthermore, when you run it, it saves the metric values, the summary metric values in the database. It keeps in the output directory. So I've been doing a lot of stuff with metric bundle groups, but just giving it an individual metric bundle. So it's a list that's just one long. So it's not really taking advantage of what a metric bundle group does. Usually, though, you want to run a bunch of metrics on any given simulation to evaluate it. So the normal way to do that is, instead of handing it a list of one, build a collection, typically a dictionary of different metric bundles you want it to process. So here I've made a dictionary with two metric bundles that are the same, except one, the constraint is in G and the plot dict shows it in D, and the other, the constraint is the filters R and the plot dict shows the color as an R. And I just use the filters as the keys of my dictionary. And so now when I make the metric bundle group, I just hand it the dictionary instead of building that single element list, and run it, tell it what database I want it to run on and what output to put it to. Run all, as usual, calculates the values. Plot all creates the plots, and you can see it created one plot for each metric bundle. Doing it with a metric bundle group is more efficient. Doing all of them within the same metric bundle group is more efficient than running them separately, because metric bundle groups are smart about how they query the database, and they can also sort of reuse slices that are in common between different slicers that are in common between different metric bundles. For example, if I was doing several metrics that involved making a map, it would only need to run the slicer once to figure out which visits went into which slice point or tail pixel on the sky. And it wouldn't need to calculate that over and over again. It could just do that once and for all, and then run the metrics on from each of the bundles that use that same slicer. So that goes through all the basic operations of what you can do with MAF, at least for analyzing just one or comparing just a couple of different simulations. But there are interchangeable parts for a lot of these things. You can experiment with different constraints. You'll want to use different slicers. You want to calculate different metrics. So you need to be able to look through MAF to understand, okay, so what can I actually use? So the first important thing is you need to know what columns are available in the observations. So what OpSim actually produces, and you can actually query the columns using the get column names from the OpSim object interface. And so this just gives a list of the column names. And you can look, and these are all the different things you can cut on or slice on or calculate things from. In addition to these things produced by OpSim directly, MAF provides something called a stacker. So a stacker is a way of calculating a derived column based on existing columns. So you'll see in here that hour angle is not included, but hour angle would be fairly simple to compute from the time and coordinates, and the hour angle stacker knows how to do that. And so you can actually specify HA as a column, and math will recognize, oh, there's a stacker that calculates HA. I can just go ahead and call that stacker after I've loaded the data from the database and use it as a column. And so here we can get the hour angle histogram just by using hour angle as our column name. Now, to get a list of the stackers that are available, it's a little more complicated. This cell shows a mechanism for doing that. These are the classes that implement the stackers. These are the columns that you can that they derive. So you can get aperture magnitudes, you can get parallactic angles, all sorts of things. And these, from the point of view of slicers and metrics, these look just like any of the things included directly in the OpSum output. You can also explore what different slicers are available to you. One particularly useful slicer is the Unislicer. So as I mentioned in the top part, a lot of different metrics follow the pattern of divide things into subsets, then calculate things for each subset. But sometimes that just doesn't make sense for your metric. Sometimes you just want a metric that calculates something based on all of the visits together. The Unislicer does that. The Unislicer is a slicer that just makes one slice that includes everything. And so it's a placeholder that you can put in when you don't actually want to slice. And these are all other slicers that you can use to divide your data. Many, but not all of them, include default plotters. You can do the same kind of list to get a list of the metrics that are already made. So this command is much like that one, and it'll similarly just give a list of the different metrics there are. For metrics, though, you can do something a little more elaborate. And this command, the base metric help doc equals true, will actually list all of the metrics and the short doc string documentation for each of them. So these are all metrics that have been predefined that are included within math now. And that makes up the rest of this notebook. Now, for most things in math, it's not included right now. Well, it's not complete. We haven't gotten documentation in everything, but in most slicers and other things that you're interested in, the usual help parentheses math dot whatever will give you a help string. So if you're wanting to know more about what the Unislicer is or what the movie slicer is, you can do a help Unislicer. Okay, so that is the first tutorial notebook. So questions, comments? Was everything clear?
Yes, definitely.
So I can go on to a second notebook.
Just a second, Eric. I think I can't raise my hand, and I just see because that's probably because I'm co-host. I think Joko made me co-host. I do have a question. Sure. That's really good. Thank you. That was a really clear introduction. I'm also happy to report that I followed along at home and executed everything on the IDF. So it's good to know that that's also working on the IDF. At the end, you've got this base math.basemetric.help, and you say these are all the base metrics that are part of math. I guess by base metric, I'm I'm assuming that you mean these are the metrics that have been defined and computed as part of the SIMS team has done and made available to everyone. Does this include all the metrics that have been defined by the science collaborations, a lot of the ones that we were talking about yesterday?
This includes all of the metrics that are incorporated in the Rubin Sim.
Okay, which also includes metrics contributed by science collaborations.
Yes.
Okay.
There is a question from Sarah Bonito. Can the list be forced? Can be forced with a predefined order to be with a predefined order?
Which list?
Maybe Sarah can chime in to explain what she meant.
Yeah, thank you. I mean, using the base metric list with the last command that you explained, like an alphabetical order, just to check if there are metrics that can be interesting for our case.
Oh, I believe they are already in alphabetical order. If you look at where it starts,
Yeah.
If you use the tuple math base metric registry mechanism to give yourself a list, that's just a plain Python tuple that it gives back. And so you can sort that however you want to just look at the list. And then once you know the tuple you're looking at, once you know the name of the metric you're interested in, you can just do help on that particular metric.
I've tried to run this in Data Lab, and they are not in alphabetical order. They are a lot. So the idea is, if we don't know in advance which one we want to use, it will be easier to have an order.
Okay. Yeah.
Yeah.
So the easy way to do that with the current code is to just use this to get a tuple that lists all of yours, and then sort the tuple as you prefer.
It's interesting, Sarah, that you say it's not in alphabetical order on Data Lab. It is on the IDF.
I mean, it is like here, if you see here, the cell 48, the output. No, I mean the previous one.
Mm-hmm.
Yeah, the one that uses tuple.
Yeah, like the base slicer. It is the same. I've just changed in the base metrics, and the list is like here, not in alphabetical orders, and there are a lot. So just to, if you don't know in advance the one that you want to use, you have to check there.
Yeah, you can use the Python sort functions to sort your tuple you get back, because what math base slicer registry returns is what this command returns is just a tuple, or you can make it a list, and you can sort that however you like.
Okay, thank you.
So I think we're about a little over halfway through the time, and if there are no more questions on this, I can at least get started on the second notebook, which is on how to write your own metric.
Sounds good.
Thank you, Eric.
So notebook 2 is writing metrics. And once again, I'll have to say which kernel you want. You want the 2021 1013 Pi 3. At least right now, that's what the current one that works is. The beginning of this notebook resembles the last one. This is some stylistic stuff that if you don't know you want it, you don't want it. You import Rubin Sim the same way you did before. You set a baseline just as you did. You get the baseline just as you did before. You set an output directory just as you did before. And I define the interface here. So if you look back at what we just did in our previous thing, what I said was what the metric does, what the metric object does. If you jump back to the previous on the metric that plays this technical, the metric by the technical meaning that plays this role in a metric bundle. What that does is it calculates a value for every slice. So what does that look like? Well, you can start by looking at what existing metrics already do. There are some handy Jupyter Notebook introspection that will help tell you about existing metrics. There's also documentation for existing metrics here. The p-info will give you things like what the parameters are. What I'm really interested in showing you here is p-source, which actually gives you the source code of existing metrics. So let's look at a particularly simple one, just a sum metric. It takes some value when you instantiate the sum metric, you give it a column that you want to sum, and then the value for any given slice is the sum of the values for that column for all the data that fell in the slice. And if you look at what is actually going on in the definition of the class, it's derived from a base metric, which provides stuff that's common to all metrics, and it defines a run method. And the run method takes a data slice and a slice point. So remember, this is run once per slice. In this case, we don't care what the slice points are. It's never used, but we need to include it as a parameter. The data slice is a NumPy rec array with the data that was queried from the database. So it's one record per visit that falls inside the slice. So here, the sum metric is just NP sum, and then the values of the values in that column. So to get a further idea of what's going on, let's create a sort of a dummy metric that doesn't actually calculate anything, but rather tells us what it's called with. So in general, metrics need to know what columns they're going to use. That's how the metric bundle knows what to query the database for. And so in my example metric here, you call the initializer the superclass and tell it I want to use the RA deck and hour angle. Notice that I'm using a stacker here. Stackers look just like any other column from the point of view of a metric. I also set the metric name, which is used in things like creating file names. And then I implement run, but include a bunch of print statements so I know what it was actually called with. And because a metric needs to return a value, I just return a random value because I don't care about the value in this example. So I build a slicer. I build a 1D slicer with huge bins so that I can get just a few values and don't get overwhelmed when I run it. And I run a metric bundle group just like I did in the example in the tutorial 1. So I instantiate my test metric. I create a metric bundle with this metric, a slicer. I don't apply any constraints at all, so it's just an empty string. And I give it an example run name. Use metric bundle group to run it, and then I run all, and let's see what pops out. So it's a data slice. So the first argument is a NumPy rec array with the fields that are requested in it. So I had RA deck, field array, field deck, and hour angle, and I had a slicer that used air mass. And so when math ran it, it retrieved field array, air mass. You'll notice that it included the LST because it needed that to calculate the hour angle. So what the NumPy array that you get includes all the columns you've asked for, plus the stackers you've asked for, plus anything needed by the slicer, plus anything needed to calculate the value for the stackers you asked for. And finally, the second argument that it got, the slice point, gives a dictionary of values that tell you the parameters for the slice that you're computing the metric for now. And so we can verify that, yes, we've generated a random number for each of our slices that we used. So when you're developing metrics, it's often helpful to just have a notebook where you can run it over and over again as you're adding things into your run method. Lynne has put together a new metric workbook, which is just a workbook. It's a Jupyter notebook that has a set of cells that are useful for just running your metric over, running a metric and refining it. Earlier, I mentioned the Unislicer. This is an important thing to know if you're developing a metric, that just you want to use all of the different visits, at least all the different visits that fit your constraint. You can still limit it by filter or whatever mechanism, whatever you want to filter with the constraint. But you can see if I run my sample metric that just tells it what it got, it gets one slice and it has all 2 million visits. And the plot dict that gives the slice point doesn't say anything useful because there's nothing useful to say. Many metrics are very general. Things like the median metric will just take the median of some column. And you may well want to do something similar. The base metric, the initializer of the base metric includes a call parameter, which gets stuffed into the call name member here. And so when you're calculating your metric, you can use that. So if you have something that can be applied to any stacker or column, it's often helpful to just rely on using the call name to set that and then do whatever calculation you want with it. So for example, here when I create my metric, I specify all the column I want is the moon altitude. And so this isn't a particularly scientifically useful combination of slicer and metric, but it just shows, okay, I can calculate the median moon altitude for any bin of air mass, for example. So typically, the values returned by run, the metric values are scalars, or so floats, integers, something like that. And the various plotters that have generally only work when you're handing back when you're returned individual scalars. But metrics can, in principle, support any arbitrary Python object. You can return anything you want. So this example shows, okay, let's build our own Python class to represent the horizon coordinates of the moon. In real life, this isn't a very useful thing to do, but it shows an example of just using some arbitrary Python object. So let's build our own class here, and let's build a metric that returns that class. So the initializer does something very similar to the other one. It sets the columns, it sets the metric name, and if you're not handing back a scalar, the metric data type should be object. And then you can define a run, which builds that object. So remember, this is a NumPy array. Data slice potentially has many visits in it, but just to have some object that I can use, I just take the altitude azimuth of the moon of the first visit in whatever is in the slice, build my funny object and send it back. And when I build a metric bundle with it and calculate the metric values, you can see that I get this NumPy array. It's an object type array with members that are the instances of this bespoke class. But when I go to try plotting it, it can't handle it because the plotter doesn't know how to handle non-scalar values. There are, however, what are called reduce functions. So a reduce function transforms the return of the run, so the actual thing you return from the metric, the actual metric value, into scalar values. So you can add members, you can add methods that begin with the string reduce that take a metric value and return a scalar from it. And you can, the key that math uses is looking for the reduce in the start of the method name. And if you add these reduce functions, run the metric exactly the same way as you did before, all of a sudden it finds our two scalar values that were created by applying these to the results of that. And if you look inside the bundle deck, if you look inside the bundle group, so when you create this bundle, when you create this bundle group, inside the instance of bundle group, there's a member that's called bundle dict, which is just a dictionary of all the bundles. Normally, it's created from this. Well, if you give it a dictionary here, it's just this dictionary. If you give it a list, it invents keys for the different members of the list and creates a dictionary that way. If they're reduced values, however, it adds things to that dictionary. And so the bundle group.bundledict.keys will give not just the bundle group that you initially created, but also two derived bundle groups that were built using the reduce functions. And so now, if you actually look inside those, you have metric values that are scalars. And so therefore can be things that can be plotted in the normal way. So any questions about that? Okay. I will continue then.
We have about 10 minutes before our break.
Okay. So one last thing I want to go over, so it's probably a good last thing to do before the break, is talk a little bit about spatial slicers. So spatial slicers work the same as any other slicer, but the slice points are a bit more complicated. They include, well, the SID is actually the HealPix ID for the HealPix map used to the slicing. You also get the end side used for the HealPix slicing, and you get the coordinates of the center of the heel pixel. So one useful thing for writing metrics is to look at examples of existing metrics. So what I've done in this notebook, rather than define a new one, is just show the source for the extragalactic M5 limiting magnitude. So it's extinction corrected limiting magnitude. This shows one last feature that really only makes sense for spatial slicers, and that's maps. So you can specify that you want a map in the, well, you specify a list of maps you want when you call the super to call the base class of the initializer for the base class, you specify maps. So in this case, I'm saying I want the dust map. And so the metric now, if asked by the metric, when asked by the metric bundle or the metric bundle group, it will be supplied with not just the normal parameters of the slice, but also values taken from that map. So in the run here, you can see, oh, I'm just going to run the M5 metric on the data slice. So this particular metric reuses the code from the M5 metric, and then it applies an additional correction to it that corrects for the dust. So the slice point, if it was given if it was given the dust map, includes an EBV point, an EBV value. So this actually applies the extinction correction and returns it. And just like you could with slicers and metrics, you can use the help doc equals true and get a list of the different maps that are available, which include the extinction, the galactic coordinates, stellar density. And the list of columns and stackers you can use are the same as I showed in the last one. So I think this has reached the end of this notebook. And we're about at the end of the time. So I hope this has given you some idea of how to write metrics. So questions?
I have a physical hand up because I can't put a virtual one up.
Okay,
I don't know who's chairing, and if anyone else has questions, I don't want to be a hog.
I'm sharing it and I don't see how to fix it. You are co-host.
No, you can't fix it. It's a feature. If you're host or co-host, you cannot put your virtual hand up.
All right.
Well, now that you've spoken, I can see your image. Just
Yeah.
zoom.
Okay, that was really nice. Thank you. That gives me a really good starting point to write a metric. Thank you. I'm very excited about trying this. I have two questions. The dust map, for example, you specify here the map to use. There's various different dust maps, as you point out. Can these choices be passed as configuration options so that you don't have to not hard code them into a metric? For example, this co-added, this galactic, extragalactic M5, you might want to run it with different dust maps and look at the differences.
Yeah, so I don't know in detail about how the maps in particular work. So remember, I'm not the developer for this. So then the mapping is sort of getting to the edge of what I know well.
Okay.
In general, when you're creating metric classes, the initializer for the class, for the object, you can make whatever parameters you want, so that when you instantiate it, you can add whatever parameters in that you want, and then you can pass whatever, you can process them and then pass them to your pass them upward in the when you're calling the initializer of the superclass. So you could, for example, instead of using collide M5 metric, you could just have this xgal M5, but instead have a flag that says use extinction map, and then only pass the map upward if it's true, for example.
Okay, maps is just an example because you just did that. It doesn't actually, it's not specific to maps. It's more about, is there a facility to define a configuration information in a file that can be read at runtime?
Not that I know of. I don't think so, but because you can define the initializer, you can put whatever you want in there. There is a mechanism, well, it's more of a, rather than a mechanism, it's more of a established pattern of behavior that is common in writing things for math, is when you'll notice that when you're creating, let's go back to the first one, you notice when you're creating metric bundle groups, sorry, when you're creating metric bundle groups, there's this dictionary that gets passed, or in this case, a list, but in general, it's a dictionary. What often happens in math, in math, is that you define a function that makes that dictionary. And so it's a pretty normal thing to do to write a function that builds a bundle dict, that if there's a set of metrics you want to run together. So for example, if you're looking at the math outputs that are provided already that are run by default, each of those has inside math a function that says this defines a bundle group, or a bundle group with these bundles in it with these parameters. So in that case, you have a set of metric bundles with parameters in them defined inside one block of code. So it's a way of setting a default. But that's not in a data file, that's still in a code file.
Okay.
But there's no reason you couldn't have that particular function call a piece of code.
Yeah.
Read it from a file.
Sure. No, I know I can just, tell a metric to read in a file.
Right.
I could write that piece of code in there. I just wondered if there was something that was part of the architecture that had a defined big file format, the same way that Science Pipelines does, which you may or may not be familiar with.
Yeah. No, there's not. The way they've been doing it is defining it inside code that builds the bundle dicts.
Okay, all right, I'll take a look. I'll give it a try and take a look. The other question I have is about plotting. It looks like you're using matplotlib behind the scenes with all the plotting. Is there? Is it interchangeable? Can I interchange the plotting library to use a different backend plotting library? Or is matplotlib hard coded into a lot of the plotting routines that are in math?
Matplotlib is currently pretty solidly hard coded in. At least the facilities that do things like combine plots together.
Okay.
Rely on it being matplotlib. So if you'll notice, there's a third tutorial called plotting.
Ah, yes.
Okay, bring up.
Yeah.
And when you're writing plotters, it takes a matplotlib figure ID as an argument, and it returns a matplotlib figure ID as an argument.
Okay.
And that's how it handles overplotting and things like that. On the other hand, you can use alternate plotting packages directly on the slice points and metric values, because you have access to all that data directly.
Sure. No, I can see it even in the first one with preparing tutorials that it returns the data set, so I can take the data set and use any plotting library I want.
Right.
But I just wondered if AFW display, you might know you can configure the backend for.
No,
like that.
Currently you can't configure the backend. I would also
eating, Eric, we are eating into our break time. So
okay.
Can you quickly take a look at chat? There is one or two questions that we haven't addressed yet. If you can just provide very brief answer, and then I'll stop recording and we can have a little break.
Okay. Oh yes, there are several questions in here.
Okay, I propose the following. I'll stop recording and you can either answer it in real time or you can type it in chat. The Zoom connection will stay on. I'm just stopping recording.
Okay.